Imagine the universe as a grand cosmic firework, born from a single brilliant point. For billions of years we thought this explosion was slowing down. We imagined that the gravity from all the stars and galaxies, like a cosmic string, was gently pulling everything back together. We pictured a future where the expansion might halt or even reverse in a great crunch. But what if we were wrong? What if, instead of slowing, the universe is hitting the gas pedal, accelerating faster and faster into an unknown future? This is the startling reality our telescopes have shown us. The question that keeps cosmologists awake at night is simple, yet profound. Are we sure we know what's driving it? This cosmic acceleration is one of the biggest mysteries in all of science. We've given a name to the force we think is responsible: dark energy. It's a placeholder, a label for our ignorance. We believe it's a kind of anti-gravity, a mysterious pressure embedded in the very fabric of space-time itself. It doesn't pull things together, it pushes them apart. On the grandest scales, where the gravity between distant galaxies is weak, this gentle but persistent push becomes the dominant force in the cosmos, driving everything away from everything else at an ever-increasing speed. It's an invisible ocean, and our galaxy is just a tiny boat on its expanding currents. So we have a name for this cosmic accelerator: dark energy. According to our best model, it makes up about 68% of everything in the universe. That's a staggering amount of something we can't see, touch, or detect directly in any laboratory. It's a ghost in the cosmic machine, its presence inferred only by the effect it has on the whole system. This idea, while it fits our observations, feels a bit like a fudge factor. When your equations don't match what you see, you can invent a new term to make them work, and that makes many scientists deeply uncomfortable. It's a solution, but is it the right one? The problems run deeper than just a gut feeling. When physicists try to calculate how much of this energy should naturally exist in the vacuum of space, based on quantum field theory, they get a truly wild number. The predicted amount of vacuum energy is 10 to the power of 120 times greater than what we observe. That's a 1 followed by 120 zeros. This discrepancy, known as the vacuum catastrophe, is arguably the worst theoretical prediction in the history of physics. It's like predicting a building will be as tall as the observable universe and finding it's only as tall as a single bacterium. Something is profoundly wrong in our understanding. Then there's what we call the coincidence problem. Why now? We just happen to be alive during the brief cosmic twilight when one is handing over power to the other. It seems like an incredible coincidence, and physicists are always suspicious of coincidences. If dark energy is just a phantom, then what could be mimicking its effects? One of the most popular alternatives is that Einstein's theory of general relativity needs an update. This idea is known as modified gravity. For over a century, general relativity has passed every test in our solar system, but perhaps it behaves differently on scales between galaxies. Imagine gravity over millions of light years becoming slightly weaker than Einstein predicted. That subtle weakening could create the illusion of an accelerating push, galaxies drifting apart faster without dark energy. What if we live in a special place in the universe? This is the core of void theories. Our galaxy might be near the center of a colossal cosmic underdensity, a void hundreds of millions of light years across, with far less matter than average. From inside this bubble it would look like everything is rushing away, creating apparent accelerated expansion. It's a cosmic optical illusion. Then there are exotic ideas like emergent gravity. Instead, it emerges from quantum interactions of spacetime, much like temperature emerges from atomic motion. Dark energy in this view is a side effect, a kind of thermodynamic friction in the cosmos. What if the strength of gravity, the mass of an electron, the speed of light has shifted over billions of years? It would mean the laws of physics themselves might be evolving with the universe. Despite these clever alternatives, the case for dark energy remains strong, built on multiple independent lines of evidence. The original supernova data from 1998 was just the beginning. The most powerful supporting evidence comes from the cosmic microwave background, or CMB, which is the faint afterglow of the Big Bang. WMAP, Planck. These maps show us a snapshot of the universe when it was just 380,000 years old, and by studying the patterns in this light, we can determine the universe's ingredients. The data tells us, loud and clear, that the universe is composed of about 5% ordinary matter, 27% dark matter, 68% dark energy. Another piece of the puzzle comes from studying the way galaxies are scattered across the cosmos. This large-scale structure is not random. Galaxies are arranged in a vast, intricate network called the cosmic web. with immense clusters, long filaments, giant empty voids. The specific way this web has grown over billions of years is extremely sensitive to the cosmic tug-of-war between gravity pulling things together and dark energy pushing them apart. When astronomers run computer simulations of how this structure should evolve, the models that include dark energy provide a near-perfect match for the galactic maps we observe today. Without dark energy, the simulations just don't look right. Furthermore, scientists have used a technique called baryon acoustic oscillations, or BAO. These are like cosmic fossils, giant ripples of pressure that were frozen into the distribution of matter in the early universe. We can see the imprint of these ripples today as a subtle preference for galaxies to be separated by a specific distance, about 500 million light-years. By measuring this standard ruler at different cosmic epochs, we can map out the expansion history of the universe with great precision. Once again, these measurements point directly to a universe that began accelerating a few billion years ago, perfectly in line with the dark energy model. We stand at a crossroads in our quest to understand the universe. New observatories both on the ground and in space are being built with the express purpose of mapping the universe with unprecedented detail. The Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, the Euclid mission. They will survey billions of galaxies, charting the expansion history with exquisite precision. They will test Einstein's theory across cosmic scales, looking for the tiniest deviation that could signal the presence of modified gravity. We are like infants just beginning to open our eyes, catching our first glimpse of the vast, intricate, and baffling cosmos we inhabit. The search is on, and the universe is waiting to tell us its secrets. Subscribe to our Universal Universe channel for daily cosmic adventures, and don't forget to share and like the video.